Our next unit is on exponential functions. So we're going to start by reviewing properties of exponents, starting with exponent laws. Now I know that you remember the multiplication, division, and power law, but what I want to show you today is why these things work. Now, one thing to keep in mind when we're using these laws, for multiplication and division, the base has to be the same in order for this to work, in order to put the exponents together. Okay, so the base has to be the same. Now, for the multiplication law, what we're saying is a to the power of m times a to the power of n is equal to a to the power of m plus n. So we're adding the two exponents. Now, the reason why this happens, a to the power of m, what that really means is a times a times a, and so on until you have m number of a's. So if m is, for example, 5, we would have to have 5 a's that are multiplying. Then we're multiplying with that. We have n number of a's. So let's just say a times a times a. So we don't know exactly how many that is right now, but there are n of those. Now, just looking at it expanded like this, so remembering that exponents mean that we're multiplying the base that number of times. So how many a's do we have in total here? A times a times a, so on, for m number of times, and a times a for n number of times. So what that would work out to be is that you now have m plus n number of a's. So that's why the multiplication rule works. So the division rule states that if we have a to the power of m divided by a to the power of n, what we end up doing is subtracting the exponents. So keep in mind again that the bases are the same. Now if I expand the same way that I did the last time, so a to the power of m, so a times a, and so on, m number of times, that will be divided by, so a to the power of n, again, we're multiplying a number of times. We don't know exactly how many this time. So what happens here? Now remember with division, because everything is multiplying in the numerator and the denominator, so this a will cancel out with that a, and it divides to 1. This a will cancel out with this a, and so on and so on. So we can just keep pairing up these a's and dividing them. And assuming that we have more a's in the numerator, okay, what's going to happen is all of the a's in the denominator will cancel out, and we're just left with a smaller number of them in the numerator. And basically what that will be is the difference between m and n. That's how many will be left, because when we pair them up, they cancel out. So the difference of those exponents is how many a's are left multiplying. Now for a to the power of m and then to the power of n, we call that power of a power, and we figure this out by multiplying the exponents. So again, a quick explanation of why. So if I want to apply this exponent of n to a to the power of m, what this means is I'll have a to the power of m times a to the power of m. So what's happening here is a to the power of m is serving as our base with an exponent of n. So I'm going to be multiplying a to the power of m a certain number of times. Again, how many times we don't know, because we don't know what n is, until finally we have done this n number of times. So if n was 5, for example, we'd have to have a to the power of m multiplying 5 times. So what we have now is we have a to the power of m n number of times. So think, if there are n groups of m objects, how many do you have in total? Well, that would be m times n. So because we're multiplying here, so we can use our idea of the multiplication rule, we are adding m n number of times, and that's what the definition of multiplication is. So some other properties we have to know in addition to the exponent laws. If a fraction has an exponent, you'll notice that I have the fraction in brackets here and the exponent is on the outside. The exponent applies to the numerator and the denominator, so that's something we have to remember. Now what we have next here, we have a negative exponent, and the way that we can make this a positive exponent, and this is going to be very important, is that we have flipped the base, or it has become the reciprocal. So I'd like to spend a little bit more time in class talking about why that happens. So just for now, if we have a negative exponent and we want to turn it into a positive exponent, you have to flip the base or find the reciprocal. Now the last exponent property that we need to remember, b to the power of 0 is equal to 1. Okay, so that works for any base except for b cannot be 0. 0 to the power of 0 is kind of one of those undefined things. But anything else to the power of 0 is equal to 1. And again, I'd like to talk more about that in class.